Hi everybody. It's been a long and really awesome day, so thanks for having me. I have a ton of slides to go through, so if you could lock the doors in the back, keep everybody in here. I'll try to talk slow but move fast through them. If either of those are wrong, I'll be one side or the other of my time, I guess. So I'm going to talk to you about building unstoppable apps on IPFS. How many people came into this conference knowing IPFS before? Okay, some of you, that's awesome. So I figured maybe as a prelude to even talking about building apps on IPFS, I could talk a little bit about what IPFS is and why it's cool and why it's interesting. I work for a company called Textile. We're a sort of research lab. We're trying to figure out what the future of personal data looks like on the web. We all are kind of individually aware of how messed up the model of personal data is right now. And my company, we think that decentralization is one of the key ingredients to fixing that model. But we're not really sure what that future looks like yet. Ideally, what we want to build is a future where we have an iCloud that we actually own, that developers can build products for each of us that respect our privacy and give us choice and the ability to do what we want with our data without sacrificing so much of our lives. A lot has changed on the web, right? What used to be an email or a nickname is now your dating preferences, your sexual orientation, your family behaviors, and everything in between a nickname and all those things. And they're all becoming your digital footprint. We need to figure out what a new future of technology looks like for those things. So when we were trying to figure out the early first steps to do this, we came across IPFS and we said, okay, that's a really interesting model and it changes a lot of the ways that you can think about the internet. So I want to set the scene for IPFS and why it was even created, why it's even being developed and why people are excited about it. And through that, I'll tell you what IPFS does. So the internet today is broken. It creates so much value for us, we sort of ignore the brokenness of it, right? And because it is a really valuable thing. It's probably the most valuable technology we've created. But it's inefficient, it's centralized, and it's just broken. So inefficient, there's a lot of examples of this, but one that I've talked about a couple times today is the model of video delivery, right? So anybody who is watching Game of Thrones, if you were watching it and your roommate was watching it at the very same time, you both had to go get that video from some server located in Europe to download that full data all the way to your router duplicated. And if your neighbor was doing it too, that was a third time multiplied across all of Portugal, all of Europe. It's become very centralized, so this has been the pattern for the last 15 years at least, that things have been centralizing. There's a lot of convenience in centralizing our internet technologies, but the consequences maybe aren't something that we want to live with long term, at least not the way that it's working out right now. So think about some of the technologies that you interact with every day. It's something like 1.5 billion people, maybe more, maybe that's an old number, 1.5 billion people on Gmail, 1 billion plus people on Instagram. Not as many, right? So it's, I forget the number of Alexa devices today, but in quite a few households. And so those are just 3 companies with 3 products. But on the other side of those products are platforms that if you're building internet technologies, you probably are touching at least one of these. And so you think about the reach of these 3 single companies into the patterns of people and into the data about what's going on in the world, and it's really significant. And so we need to make some conscious decisions as a society if that's where we want to go and how much of that we want to allow. And so the brokenness touches us in a lot of different ways. And so the brokenness of the internet can touch us in personal ways. And so if there are any of the people that ever use GeoCities, the idea of a project like GeoCities that had such a personal outlet of data just going away was pretty significant. Even more than that and more recent is Cambridge Analytica, right? Very personal implications of having so much data controlled by a single company that if that company makes one bad choice or one series of bad choices, we're all sort of the victims of that. It has technical implications, right? And so we've all experienced services sunsetting. So the things that we're building on or the things that we're touching every day going away or being planned to go away. This is a number that was new to me recently that I thought was just amazing. So in the US, we have the Supreme Court, the highest court in the land. They make decisions about how our law should be interpreted and how we as a country should run that are really, really important. And a study found that 50% of the links in their decisions, so URLs in their decisions, 50% of them were broken. They didn't even go to the things that they were pointing to anymore. And so you're talking about a historical record that's really important for how we're making decisions at a national scale, and the data's just gone. Has social implications, right? So we see things like entire communities disappearing. We see things like governments being able to stop internet completely or wall it off completely. And we see censorship of specific outlets on the internet. And so this one I want to bring up, kind of focus on it because I'm going to talk about it a little bit more later. But if any of you aren't aware of the situation in Turkey, so 2 years ago, they found that on the state-sponsored terrorism page on Wikipedia, it listed Turkey. It listed Turkey among a lot of other countries, including Great Britain, the United States, a lot of countries that have done this in different ways. And they said that that was actually the media lying to the people. And so told Wikipedia they had to take it down. Wikipedia obviously said, no, we don't take that stuff down. And so they said, okay, then Wikipedia is shut off in Turkey. So the creator of IPFS once said this, and I really like it. The internet is the planet's most important technology. And so if it's the planet's most important technology, how are we allowing it to sort of unfold this way? And can we be proactive in thinking about the future of this technology and making it so that these things are less harsh, are fixable? And so that's where IPFS came from. So this was mentioned in the first talk, which was really exciting to me. But IPFS is always called IPFS, but behind those letters, it means the Interplanetary File System, which is such a beautiful name, and it gets your imagination going about what it means to exchange data and information at a planetary scale. But really, it solves some things today for the way the internet runs right now. So IPFS is a distributed network of peers using peer-to-peer protocols. It's self-organizing. It's a resilient network that lets us do things differently. In short, it's a replacement for HTTP. So HTTP is the model by Tim Berners-Lee where you want to request something so you know the server, or you at least know the address that can get you to a server that has that information. IPFS doesn't work that way at all. And by replacing HTTP, we can actually reimagine a lot of other things about the internet and how the internet runs. And I'll get into that more. But so how is IPFS different? So IPFS is verifiable, it's trustless, it's decentralized, and it's resilient. And there's a lot of really cool concepts that are in the IPFS technology, and I don't have time to talk about each of these today. But one that I am going to talk about is the content addressable piece of it. And so I mentioned before how HTTP works. You know the address of some content that you want that's going to map you to a server that can get you that content. And IPFS works fundamentally differently, and I want to dig into that a little bit and share that with you. So content-based addressing. How many of you are familiar with this? Awesome. Okay. So for those of you that have touched IPFS before, this is a really important piece for how it works, and it's also really exciting and interesting. So alternative to content-based addressing is what we call location-based addressing, right? It's the URLs that we're all very used to. And so in location-based addressing, right, you have a URL for some JSON file that you want to get. So you take that URL on the client, you go to some DNS server that can translate it to an actual server in the cloud or in somebody's office. So then you get the server, you go to the server, it can translate the path goes to the original file, and I get this piece of JSON back, right? And then it comes back through the tubes, and I have what I want. But this is where a lot of that brokenness comes from, or at least one bucket of that brokenness comes from, is that each of these transformations that happens between me and that JSON file that I want to get is susceptible to being broken. So at the DNS layer, you have censorship. At the server layer, you have sunsetting of entire APIs. And at the file layer, you have just pure link rot. So where people think the URL might still exist, it just doesn't. And people, you can't monitor files at the human scale. And so back to the Wikipedia example, this gets really interesting because, okay, so you're this user in Turkey and you want to read some page on Wikipedia, so you go to look it up and sorry, the government has blocked it. But content addressing means that you're not actually requesting a URL for the file, the whole URL of this file on Wikipedia. Instead, you're asking for a fingerprint to that file. And so how does that work? That's called content-based addressing. So you take a file, you take this z.json, and instead of saying, oh, I'm going to give you the URL for where that thing exists, you take a hash function, and what's pretty common is SHA-256, and you get the hash of that file. So a totally unique hash for this JSON file. And then anybody that wants to request it by that hash. Not by a URL on the internet, but just by the fingerprint of that file. And they can request it from anybody else that's using IPFS. And there's another piece of technology that I won't go into today, but that can help route you to the person who does actually have that file. And so the network is going to get you that data back. And so instead of going to the single Wikipedia web page and getting blocked by the government, you're going to go to the network of you're going to go to the network of IPFS users. So this is the piece I can't really go into, how they route you to the file. It's called the distributed hash table. It's worth looking up if you want to spend more time digging into it. But so instead of going directly to the Wikipedia web page and having get routed to the server that you're actually getting blocked, you just go out to the network of IPFS peers and you say, I'm looking for this hash, I'm looking for this file, which might be a web page on Wikipedia that you want to read about. And any one of them can route you through the network to the original file and get it back to you. And so the government can't censor you anymore. And this is exactly what happened with Wikipedia in Turkey. So now in Turkey, there's a copy of Wikipedia that's hosted on IPFS, and anybody who wants to read the Wikipedia pages can go read them through any IPFS gateway, which can still serve HTTP, or they can read it through using their own IPFS peer. So back to how it's different, I just want to go over these again. So it's verifiable. So verifiable, when you have that unique fingerprint of the file, what's really great about that is that when you go and request it and somebody gives it back to you, what happens if they give you back a false piece of data? You just rehash it and it's not going to match. So you know exactly that they gave you the thing that you asked for. And in that way, it's trustless. You don't care who gave it to you. As long as they gave you the thing that you asked, you got what you wanted. And it's decentralized. You can ask any peer on the network. And it's resilient. You can cut off arms, and it doesn't matter. You can route around what people are thinking they're blocking. And so there's a lot of people trying to build cool things on IPFS now that go beyond just hosting web pages, but are thinking about how you can connect with people differently. So a few of them, Decentralized is a game it's a world built on Ethereum really, but they use IPFS to distribute the assets for that world. Anytype.io is exactly what they say. It's the dashboard for anything. It's where you can create to-do lists and collaborative documents and upload your files and videos. And OpenBazaar is a peer-to-peer marketplace. So it's the eBay of peer-to-peer. So there's no intermediary when you want to sell something. You just buy it from the person who's trying to sell it. Textile Photos is an experiment of our own. It's for backing up and sharing your own private photos. And so for us, thinking about IPFS was enough for us to really start imagining what the future could look like for personal data. Imagine your data is encrypted on a system like this where nobody can tell you you can't have it anymore. Nobody can sunset the API that you had put so much time in building your photo albums behind. And nobody can stop you from connecting with peers that you want to connect with. And so to bring it to the real level, last weekend, so I'm going to a conference next weekend that's all about IPFS. And so I thought between Commit Porto and this IPFS camp, it'd be really fun to build a small experimental game. And so I built this game, it's called IPFS Tag, and it's real world peer-to-peer tag. And so the only way it works is you actually have to physically interact with people, but then there's a digital shared record of the game. And so I'm going to walk you through how that works in the IPFS world. So let's build a game. If any of you want to download it, this QR code for the next few slides, if you can scan it from your phone, you can open up the link to download the game. So yeah, what does it take to build a game of tag? Oh, and all the methods in here, we have some documentation, and our blog post has a lot of write-ups about how inside IPFS is working, worth reading, but you can start at the docs. There's some good intro material. So a game of tag, what is a game of tag? You have basic identity, right? You wanna know the other people in the game. You have information sharing, right? Like when you're on the playground, somebody would yell, "So-and-so's it," and you'd all, you'd run from them. You have the rules that you agree by and the rules that you can kick people out of the game when they're not playing by. And you have verification, right? You have a way to know who did the tagging and that somebody's not claiming to not be it anymore and then pulls their hand out of behind their back and tags you. You can't do this anymore. I just killed this game, so sorry you can't. But I will. But after my talk in the reception, I'll start a new game if you want to try this out. So using the 4 components, let's put together a game. Right. So we need the identity system, and it's purely because you want to know. Okay, like first of all, who's in the game, right? You don't want to be running around the playground tagging people that aren't actually playing the game, and you want to know that who you tagged so that you can claim it to the other people. So this is solved on IPFS by what's called the peer ID. And so this is a cryptographic identity. So every file on the network gets its own hash, but every user or every peer on the network gets a unique fingerprint as well called the peer ID. And this is cryptographic, so it's their public key. So they can sign things with their private key as well and prove that that's them. So at Textile, when we want to put things together like IPFS tag, we take that peer ID and attach metadata on the network so that you can have things like usernames and avatars. And like I said, you can sign things this way. And so, right, and so we have the peer ID from IPFS, and then we have something like a display name that we attach this metadata to. And then I'm going to go into how those identities are shared with everybody in the game, but it's using a decentralized database that we call a thread. And so in this game, it's super easy. You download the game, and inside the mobile app, you're going to have a new IPFS peer. So everybody who downloads the game now has one of these private public keys as their peer ID. And the game is just going to ask you to put in a display name, and that little piece of metadata is going to be attached to your peer ID so that other people, when they find your peer ID, have a way to then understand your short name so they don't have to be talking in 256-bit strings. Okay, so we need a way to share information, is what I said before. And so for that, we need something like a distributed database. And the reason that you want that is because you want to be able to let everybody else in the game know who's it. And you want to know when that changes hands. And so actually it's really great because we've heard a few talks already talk about append-only logs, and we've heard them talk about event systems, and this is exactly what you need for something like this. But in a decentralized network, you need to think about it a little bit differently. In the first talk, it was mentioned how the database is shared with all the peers on the network. And that's exactly the way that you can build it on IPFS. You can have all the peers track the state of the data at all times. We also have models where some peers can offload that tracking to sort of a trusted service or server. But we call these threads. They're distributed, they're verifiable, they're encrypted. And so for every game in IPFS tag, that's created, it creates this new thread, a new database. And the only people that get to see the content of that database are the people that are invited to your game. And so this is more cryptography. So every database has a new private key and a new public key, and all the data going into it is encrypted by that, and so only the peers that are part of the game get to see that. There's a lot of flexibility about how you you start these databases, and I won't go into this, but this is back to the docs piece, worth taking a look at. But threads can be connected in a lot of ways, to getting you updates about the game, to having our peers talk to each other, to doing remote storage and backup and other interesting things. But in the game, it just looks like this. Like I said at the beginning, that this game requires physical, you actually tag people. And so we have this distributed database. We have the user on the left is the user that's it, and the user on the right is the user is just another player. And any user who's it is going to run up to the person, to somebody else playing the game, and shows them this red card, and then they just have to scan the red card, and then they're it. So I mentioned this already, and when that happens, that information is propagated to everybody else playing the game, and everybody knows the change. Okay, so how does that happen in this distributed log? So the way that we handle this, and I'm going to come back to verification, is the person that tags, so person 1 here, user 1 is going to tag user 2. It isn't user 1 that's actually going to write the entry to the database. It's actually going to be user 2. So user 2 is going to write the entry to the database and sign it with their public key. And so when they do that, they're saying, I'm it. And nobody wants to be it, so everybody else can more or less just trust that. And we'll come back to the rules as well. So they write this new entry to the thread, and as soon as every other user in the game gets that update, they all understand that there's a new person it and a new person free. And so when I built this, again, it was really for the in-person, and so all you do is you go up to the card and you scan it with your camera, and I think most new phones now, you can scan the QR code and it'll just pop right up and open in the app, and then all the background pieces about updating the database all just are automatic. Okay, you need a set of rules to play a game of tag. So what are we agreeing to play? And this is where distributed verifiable systems get really interesting. You have kind of two sets of rules. You have those that are built into the technology, and you have those that are the application rules. And so threads have a schema, only certain types of transactions can happen. You have read and write capabilities. But what's really great is that verification. So in this game, I say only the people that can write new tags are the person that gets tagged. And so you don't have a bunch of people running around and claiming that they tagged somebody and those being false. And so the app can very quickly pick up on discrepancies and actually tell you that, okay, that transaction is breaking the rules of the system, and don't allow it or give a warning. Okay, so what that looks like is a bunch of little payloads about what's happening in this game of tag. So game of tag was started by user A, who then tagged C, then tagged B, and then we have some problems. So to start the game, A is it, and then C becomes it, because what happened is C got tagged, but C signed it. So everybody sees that, and it's a valid tag. Same here, now B is it. B got tagged, they signed it. Cryptographically, we know that B got tagged. Okay, this is a problem though. It says, that A was it and tagged F, but since everybody has a copy of this database, everybody knows that A is no longer it. So this is an invalid one, so they can all just throw this row out. It doesn't matter. And this one's a problem too, because it says B tagged D, but it was signed by A. And so everybody knows this is a cheat and can throw that out. Okay, so then the verification system I've talked about quite a bit, but this is where it gets really interesting, is the users actually sign each of these payloads. And then the bonus of this is that for the same reason that you can stand up websites that nobody can block, we have a game of tag that nobody can block. The game of tag, even though it's private and encrypted among the users that are playing it, it's actually on the entire IPFS network. So you can discover events, you can share events of the game through other peers. And so nobody can stop me from getting the interaction between me and you. And so if you start imagining that game of tag can be something really interesting. It can be conversation applications that can't be stopped. It can be lots of other cool things. So we have verifiable, trustless, decentralized, resilient, unstoppable game of tag, which honestly is what I always wanted. So pretty excited about that. But yeah, I wanted to kind of put that out there as an example of what you can do over the weekend, but a way to make us rethink the way that we're designing applications and interfaces. So imagining the effort that we put into building communities in Facebook events, or depositing our knowledge in Wikipedia, or our personal data and our health records, we can start to rethink the way these things are connected to the internet and the way these are owned by us through cryptography. And I always think it's so interesting that so much of our digital technology, as soon as the maintainer is gone, it's dead. And this is very related to rethinking that model. It'd be as if the DeLorean just stopped working. And so some resources for you, just to leave you. I hope that inspired you to try to build something and play with IPFS. But our blog has a lot of really great content about just how things are working, how that discovery is working on the network, and how you verify the file you got is what you asked for. The IPFS website obviously has a lot of great things. They run some educational programs. And then that's meant to say docs.textile.io. If you have any questions, we have a public Slack channel. We're always around just to talk with people and brainstorm with you. And thanks very much.
Questions? I think some people were downloading the tag game, so you can start tag game again here.
Perfect.
Over there.
Thanks for the talk. That's really interesting. You were saying that you couldn't block a specific site on IPFS like you can with the web. Could IPFS in its entirety be blocked within the country?
So could Turkey block all of IPFS?
Correct.
I don't see how. Okay, so core to IPFS is actually a protocol called libp2p. And so connections are happening directly between you and any peer, which is a really hard thing to block in any way. I mean, it would be whack-a-mole. They'd have to go and somehow block everybody who stands up a peer outside of the country. And you could essentially have internal, maybe, untenable. Theoretically possible, but untenable, yeah.
Any more questions over there?
First of all, thank you for the talk. So you mentioned that the content was addressable by hash. What happens if the hashing mechanism is deemed insecure and has to be changed?
Yeah, so they work. So IPFS works with a method called the multi-hash, and so actually every hash declares its own method. And so when you decide that your content is 256, you prepend it with a code, the multi-hash code for 256. So then anybody who gets it knows, how that fingerprint was derived and can and verify their file. But there's no reason to stop you from doing 512 today. And so people that are working on data that needs to be extremely secure can be doing just that, right? They can be changing their hash proactively. And then for outdated hashes, there's migration strategies. But for things that are really like doesn't matter. You could be even using 128 today, for example.
Any more questions? No? In that case, thank you, Andrew.